Okay, so the next talk is by Franz-Viktor Kuhlmann on pushing back the barrier of imperfection. Thank you.
Thank you. So I would like to thank the organizers for inviting me to give a talk here and also for organizing this wonderful program. The term imperfection in my title refers not only to imperfect fields, but also to what we call the defect. The defect of valued field extensions, finite valued field extensions, which can also appear over fields of characteristic 0 once the residue characteristic is positive. Now, we heard already about defectless fields and all that, so it's time maybe to remind you of what the defect is. So we take a finite extension of valued fields, and we assume that the extension of the valuation v from k to L is unique. Yeah? Think, for instance, when the field k is Henselian, this is always the case. And then we have the following equality, and it becomes an equality because of the so-called lemma of Ostrovsky. It's not the theorem of Ostrovsky, it's the lemma of Ostrovsky, which says that the degree of the extension is p to the nu times what we call the ramification index, which is VL over VK. So I follow the notation that has already been used. These are the value groups, residue fields, LV over KV, where P is, so first of all, nu bigger equal to 0, and P is what we call the characteristic exponent of the residue field, which is just the characteristic if it's bigger than 0, and otherwise we put it to be 1. So 0 wouldn't make sense here. So p to the nu is the defect, and if it's bigger than 1, then we call this a defect extension. Okay? And otherwise, so if KV has no defect extensions, then it is called defectless. So that was already used. Okay, so I said defects can also appear over fields that are perfect. Well, maybe I didn't say it, but I say it now. So examples. Defects over perfect fields. So you start with FPT, finite field with p elements, and the Laurent Series field. You go to the perfect hull. Which is just this guy, and you join the p to the nth roots where n runs through all natural numbers. So that's the perfect hull. And now you take a root, so extension generated by root of a polynomial x to the p minus x minus 1 over t. Yeah, this gives you a so-called Artin-Schreier extension, and this extension is a defect extension. So that's a well-known example, and it goes back to an example, interestingly, by Apjanka, who was mentioned in the last talk, who observed that this extension here does not lie in the Puiseux series field. So the Puiseux exponents, the denominators are growing and growing. And however, Apjanka didn't explicitly notice the defect. He never talked explicitly about the defect, although in his work it was always around. Okay, so that's one of the fields. Another one, mixed characteristics. Take QP and do essentially the same thing, so to say. And now take an analog of the Artin-Schreier extension, although you don't have them in characteristic 0, but take x to the p minus x minus 1 over p, and this generates again a defect extension. So we have two examples over fields that are perfect, which shows that the defect is not directly related to imperfection in the field sense. Okay, so but if you have such extensions, now we have the defect is P. So E and F, this is the ramification index, the inertia degree, those appearing there in the equation, they are both 1, which means V of L is V of K, LV is KV, and also that appeared already. This is an immediate extension. Which means that value group and residue field don't tell us anymore much about this extension, which has a consequence for the model theorists that relative model completeness breaks down. If you have immediate algebraic extensions, no chance for relative model completeness unless you suppress such extensions somehow by an enriched language. Okay, so the defect is a main hurdle. Problems in positive characteristic, or at least in positive residue characteristic. And one was just mentioned in the last talk, local uniformization. I will say more about that again. And as I indicated now, the model theory of valued fields. And think, for instance, okay, this guy was already mentioned. Open problem is, does it have a decidable theory? Same thing, it's perfect hull. Let me write it like this. And what we saw yesterday, okay, how about Q, P, a billion? Yeah. So such problems. What's the common underlying problem? Okay, that is the structure theory of valued function fields. So if you want to get something like model completeness, things like that, or relative model completeness, one approach to that is so-called embedding lemmas. So you try to embed, oh, I'm using this one, okay. Yeah, so you try to embed finitely generated extensions of a valued field in some highly saturated elementary extension of that field. So, but what is a finitely generated extension? Well, the algebraic extensions don't play a role here. Those cannot be treated anyway. So in the settings where we have a hope, K will be relatively algebraically close in the extension, so the transcendence degree is at least 1. And these are valued function fields. So you have, and to solve such an embedding lemma, you want to know about the structure of these function fields. Now, what about the algebraic geometry side of it? So now comes a different take on local uniformization than what Bernard told you about. Sorry? Oh, that's a saturated, highly saturated elementary extension. Okay, so in algebraic geometry, local uniformization, okay, if we don't solve a problem globally, we want to solve it locally. That means we want to get rid of one singular point. Well, we'll go to another variety that has the same function field. Now, how do we track this point in this new variety? The idea of Zariski was to use evaluation. So in order to track the one point, you endow your function field with evaluation. So you get a valued function field. Now, what do you want to get then as to the structure theory? You want to eliminate, well, that's the first step at least, eliminate the ramification. Because ramification practically is equivalent to the failure of the implicit function theory. So what does elimination of ramification mean for a valued function field? So you have f over kv, your valued function field. And it means we want to find a transcendence basis T such that the rest of it, so the algebraic extension now, the function field lies inside of K adjoint T and now the algebraic extension should be inside the absolute inertia field. What's the absolute inertia field? Well, absolute inertia fields we have seen in passing yesterday in Jochen's talk. Very quickly, the picture here with the whole absolute ramification theory, there was the absolute inertia field. So, absolute inertia field. So it's the inertia field with respect to the inertia group in the extension from a field to its separable algebraic closure. And this guy, well, you can think of the maximal unramified extension of a Henselization. Yeah, that's what we call the strict Henselization, yes. Okay. Yep. Okay, so that is elimination of ramification. And okay, what's the state of affairs? Resolution of singularities, local uniformization, and not even elimination of ramification. All of them not known. In positive characteristic 4 dimensions bigger than 3. So we have nice programs. As you know, Hironaka has a nice program for resolution of singularities. He even announced a new version on his webpage. Bernard has a nice program for characteristic blind local uniformization. But so far, these are programs. And so details have to be filled in. And whether these programs, well, they evolve. But whether they, in the end, converge to something, we don't know at this point. OK, so my own program, well, it's not really a program because I don't claim that it converges to any of these. But what I want to do is investigate the structure of valued function fields. OK, so I want to give you one example for elimination of ramification, which is non-trivial. And for that, I want to introduce something that was also already mentioned. And these are the Tame fields. And, well, in residue characteristic 0, everything is quite trivial. All fields, all Henselian fields are tame. Let me first define tame extensions. Any extension is tame, algebraic extension, sorry. Algebraic extension is tame if, now these can be infinite for every finite subextension let's say E over K V, we have that Tame extension 1, we have that the ramification index is not divisible by P. So VE over VK not divisible by P. Secondly, the residue extension is separable. And thirdly, the extension is, so E over KV is defectless. So you may wonder, think of, I think it was Franziska's talk. At this point, well, she mentioned something else. So let me first say we define Tame fields. If the extension to the algebraic closure over K V is tame, well, we want that it's Henselian and separately tame was also mentioned if, again, Henselian and the extension to the separable algebraic closures, tame. And here, okay, when you remember the definition of tame that Franziska used, she did not speak about defectless. She did not say the field should be defectless. She just said it should be algebraically maximal. But in the presence of the two other conditions, that is equivalent. And I just wanted to point out here that you can actually, yeah. Well, actually, you can drop it. Yeah. Okay, where this is understood to be an extent, I wanted to cheat a little bit, where it's understood that, again, the extension of the valuation is unique, yeah, with that condition. Okay, good. So, but we are concentrating on the defect, so it's good to know, okay, we are actually, tame fields are defectless fields. Okay, now, what can we do with that? So, an example of elimination of ramification, and it doesn't look like much. Which blackboard is this? Oh, this one here. Whoops. Okay. It's a theorem which I call the Henselian rationality. You take a tame field, and you take a valued function field that is immediate, so no change of value group and residue field. Of transcendence degree 1. Okay. Then you find an element in F such that F is not only in the absolute inertia field, but lower, just the Henselization. So this is the Henselization. Immediate, no change of value group and residue field. V of f is V of k, Fv is Kv.
And the function field means parallel generated.
Yes, yeah. Algebraic function field. Okay, now when you look at this, this doesn't look like much. Yeah, and indeed, if you have residue characteristic 0, it's trivial, you just take any transcendental element x. But if you prove it in positive residue characteristic, well, try it. It's really difficult. And it gives actually, it's a crucial ingredient in two main results. And these are first result, local uniformization. But not what we really want. We actually want to have the local uniformization for the function field that we are given. No, we have to change it a little bit, and we call that separable alteration. So think of Dion, resolution by alteration, meaning taking into account a finite, and in this case, separable extension of the function field. Yeah, and well, this theorem here comes in exactly in the case when the valuation on the function field is not an Apjanka valuation. Yeah, then you have some parts, and you can reduce to this immediate case of some parts of the function field. Okay, the other result, oh yeah, I should say, this is with Hagen-Knaaf. And this is advances in 2009. Okay, and the other thing is the model theory of Tame fields. Well, Tame fields and also separably Tame fields and the first one appeared in Krelle 2016. And the second one, and this is with Kuschik-Pahl, was already mentioned yesterday, and that is Journal of Algebra, also 2016. Okay, so what's the theorem here? So let me give a theorem for this case here. Tame fields satisfy relative completeness completeness, I meant, yes, completeness, relative decidability, and in positive characteristics. So if the characteristic of K is bigger than 0, then also relative model completeness. A mixed characteristic, this gets really very awkward here, and you would probably need additional conditions to get something like that. Okay, which one am I on here? This one. Okay, as I have this one free here, let me just start something here. Algebraically maximal Kaplansky fields. They have been around for a long time. So they are, what do we have about them? They are defectless, perfect, and they have uniqueness of maximally immediate extensions. Which is often a very nice tool for proofs. But they are somehow awkward. This condition about the residue field is a little bit unnatural in a way. Well, that's better for tame fields. Okay, oops. So here, tame fields. They are defectless and perfect. Perfect fields. Pardon? Yeah, and characteristic 0, everything is perfect. Yeah. Okay, so, but this ends here. To be continued. Yeah, perfect, still fine. Okay, where are we? Separably tame. Separately tame fields. So this ends here. Not perfect. I'd read it in the way not necessarily perfect. Yeah. Well, they are not defectless, but the defect is quite harmless in a way. So this also ends here. Defect only in purely inseparable extensions, not otherwise. Okay, so much for now.
How in the composition during separable and separable? If you have during separable and not separable and you compose them, you still get a defect.
Can we discuss that in the coffee? Thanks. Okay, so now, okay, we have seen tame fields are perfect. Okay, so what about our perfect hull of FPT? It's also perfect. But not tame. Too bad. are not even separably tame. Even worse. So we have to come up with something new. Okay, so questions. Can the Henselian rationality theorem be generalized? Well, it holds over separably tame fields. But how about pushing the barrier of imperfection further? So can model theoretic results be extended to imperfect valued fields, like FPT, or fields that are not defectless, like that guy? Okay, let me give you the theorem about separably tame fields. Well, in mixed characteristic, everything is done by tame fields, so this is only in positive characteristic separably tame fields have, okay, what do they have? Relative completeness. Because we are in positive characteristic, we have no problems with mixed characteristic here. Tame fields, okay, of characteristic k bigger than 0. Relative decidability. But now you run into a problem when it comes to model completeness. You really have to guarantee that the extensions you deal with are separable. And that you can do by enriching the language by the so-called predicates of P independence. So in enriched language, P independence, you have relative model completeness. So that shows one way to go, namely kick out the bad extensions by enriching your language. So the question is, how far is that possible? How far can you go with that? Okay, so
what do you mean by relative model completeness or relative completeness?
Relative to value group and residue field. So what we also call these X-Cauchy-Yershov principles.
Oh, okay.
Yeah. Okay, so separably tame fields. Not perfect, but I have one nice feature. They are dense in their perfect Hahn. Okay, well, the perfect hull of FPT, because it's perfect already, has the same property. So, okay, trivially. Now, to go further. So we have seen, I noted already, well, there is some defect here, but very restricted, just in purely inseparable extensions. And actually, these are all in the completion, these extensions. So other than that, can we allow some defects, some good ones? Are there any good defects? And now I come to a classification of defects that I have given some time ago in the Illinois Journal, 2010 to be precise. And the idea here was, okay, you have the so-called dependent ones obtained by deformation of purely inseparable. Defect extensions. And secondly, the other ones that are independent of purely inseparable extensions, so they are called independent. So I will not write the next thing down because I want to save a bit of time here. There are indications that the dependent ones are the bad guys, and the independent are much easier to handle. Indications are Michael-Temkin's inseparable local uniformization, because what he does is alteration by purely inseparable extensions of the function field, and these kick out these dependent, those that matter in that function field, those dependent defects. So that's one indication. Now, by the way, we have separable alteration, we have inseparable alteration. Do we have a common denominator? No alteration? Unfortunately not. Somehow we still have to stow away defects in these alterations. Can we push the barrier of imperfection to get it down to no alteration? That's the big problem. Second indication among many, there is a work of Katkowski and Pilton about ramification theory of valued function fields, where they have an interesting example, which is a tower of two Artin-Schreier defect extensions, where something goes badly wrong, namely strong monomialization. And then I asked the question, are these defects dependent or independent? And then Katkowski, El-Hitti, and Getzi, they showed these are both dependent defects. So obviously bad ones. Okay, so now this went also into another result, this classification, which is the following theory. Okay, suppose you want to construct some example or counterexample. You want to construct a Henselian defectless field. How do you do that? It's not easy. Okay, well, you can take maximal fields, those that have no immediate extensions, but often that is too large for your counterexample. So you need some criterion, and that use this classification if and only if it's algebraically maximal and inseparably defectless. So that means every purely inseparable extension is defectless. And I used it for giving an example in the Journal of Symbolic Logic some time ago, which shows if you take a naive axiomatization for FPT, well, there are axioms that are independent of that. So that axiomatization was not complete. And that is exactly done by constructing an example. Okay, so we would like to have something like that also in mixed characteristic. Yeah? Okay. Well, if you look at the definition here, deformation of purely inseparable extension, there are no purely inseparable extensions in mixed characteristic. So what will play the role of these purely inseparable extensions? And what's the analog of the definition of dependent? So the point is, there was a theorem in that paper in the Illinois Journal which actually connected the classification with, so we learned already, if L over K be defect and degree P, then it follows E and F are 1. So we have immediate. And then it follows that, so if L is Ka, then this set of values, A minus C, C and K, has no maximal element. And what you can do is you can take it to define a cut in the value group. Actually, you better go to the divisible hull of the value group, and you define a cut there. And now independent means the cut you get is, well, here you have your value group, you have any convex subgroup H, and then the cut is H minus, which means you take the lower edge here, you put your cut here. Yeah, so that characterizes it in positive characteristics. So why not take this also in mixed characteristic? Does it make sense? So we did that. Now I'm reporting on joint work with Anja Blaschok. So take this as a to generalize the definition to a mixed characteristic. Here I should say this only works for A being an Artin-Schreier root. We don't have that in mixed characteristic, but we can get polynomials that look like Artin-Schreier polynomials and use them. Okay. So then you have this definition, but the question at some point was, is that the right one? Yeah, so these, no, in mixed characteristic, are these dependent guys really the bad ones, and what about it? Now, an idea that came to help was when you transfer something from equal characteristic, positive, to mixed characteristic, perfectoid fields, tilting, yeah? Leading to the question, how much do we see the defects in this classification also in the Galois theory? Yeah, but at least that was an idea. Then, but perfectoid fields, they are complete, they are rank 1, so they are not first order axiomatizable, no good for me at least. So what came to the rescue is, after hints by Michael Temkin, looking at the book of Gabriel Ramiro, almost ring theory, there are the deeply ramified fields defined. If we have a condition, which I call deeply ramified for the valuation ring, saying that the Frobenius is surjective on O modulo P O, well, actually it is for completions, so for the completion of the field, and there is some strange condition on the value group, namely no Archimedean component is discrete. Now looking at that, coming from my experience with valuation theory, is a bit strange. So it's, I would say it's only almost useful. So almost useful. So my advice, relax, generalize. And that leads to KV is a generalized, or GDR, field if we have this one here for the valuation ring and condition just on VP that VP is not the least positive in the value group. Okay, but also sometimes you want to be closer to home, but home for me is the Tame fields. So you may also make more sense of this here by saying, okay, let's say the value group is P divisible, as for Tame and separately Tame fields.
This is not so good because I think you want to go to the rank 1 component to say not to this step, but otherwise.
And this I call semi-tame, which is valuation ring plus V of k P divisible. Okay, and well, then we have separately tame, semi-tame, deeply ramified, and GDR. Okay, and implications, which cannot be reversed. Same here. This is not trivial. So you really have to work for this one. These are trivial. And also you have backwards here this implication if your characteristic is positive. Okay. Now, interesting observation by this condition here. If the characteristic is positive, then KV is dense in perfect high. So all of them have this in common. Okay, what about the defects? From here on, you only have the good ones. That's also a theorem, only independent defect. And all of them have a nice feature. It's preserved under any algebraic extensions. So the hope now is to generalize theorems like the Henselian rationality theorem to at least the semi-tame case. Well, I have had notes years ago that seem to say it's true, but I lost them in all the moves, so now I will work on recapturing that. More daring, maybe all of these fields. Okay, and so pushing the barrier. Well, I have no time. There is another thing. There is one notion of so-called extremal fields. I wanted to tell you about that, but time is over. So these things are interesting for these guys. So for instance, perfect hull here, because this guy is semi-tame. And so is the analog in mixed characteristic. So maybe we can capture something, some model theory here by pushing the barrier in this direction. Whereas, and that is a class in itself, everything breaks down beyond this line. These extremal fields, there is some theory about them, and that would cover this guy, he is an extremal field. So that's work with Florian, with Saliatskin, now Dorhan, and then later with Sylvie. We have 2 papers about extremal fields where there are some results. For instance, the result, something that we saw in Franziska's talk yesterday, if you take an Aleph-1 saturated valued field, every rank 1 component not only has value group Z or R, but it's actually an extremal field. So they are abundantly in our mathematical nature, but we don't know how to piece these rank 1 components together. Okay, so finally I want to make a quick advertisement. One of the next conferences after this program is in June 24 to 29, the so-called Algebra, Logic, and Number Theory, and it's the 5th one in Bentlewo in Poland. And you can find information about that one on the Valuation Theory homepage. If you want more information, you can also ask me. Thank you very much.